Hi there, my name is Tom Barshin. I'm from the University of Calgary. So the purpose of this video is to explain some of the core concepts that underlie our paper. And I think a video might be a bit easier way to explain some of these ideas because we can use some simulations and diagrams and try to explain how things evolve through space and time a lot easier than we can in a paper format. So this is a LiDAR hillshade from the Big Stick Sand Hills of Saskatchewan. And these dunes are completely vegetated. There's vegetation everywhere. They're immobilized. They're not moving. And so what we're trying to do in our paper is we're trying to understand the key condition that is responsible for dunes hosting vegetation. And so our key idea here is that a stabilized dune field contains a wealth of information. And the reason this is because once a dune becomes immobilized by vegetation, it tends to stop moving. So we can extract some information from the morphology of that dune to help us understand what that key condition is that allows vegetation to grow on every part of the dune. So to help explain how our paper works, we're going to start with a quick simulation from the BAM model. This is one of our previous projects. I'm going to start with this Barkhan dune. I'm going to run forward in time and introduce vegetation. As vegetation is introduced, the dune is going to stabilize into a parabolic dune. So we'll run over this simulation and then we'll go back and discuss how we interpret this, what's going on here. Okay, so the dune has fully stabilized into a really awkward looking parabolic dune. Let's go back and start at the beginning again. Okay, so in this paper, we have decided to not think about dunes in terms of their sort of macro shape, in terms of being barkhans or transverse or blowout dunes or whatever types of dunes. What we're trying to do is we're trying to think about dunes as being composed of a number of dune slices. So we're going down one level in the hierarchy. Dune slices are nothing more. They're nothing more than wind parallel cross sections of the dune, and so each dune is composed of a number of different dune slices. And our key idea here is that dune slices behave with very generalized rules, and we can use these generalized rules to predict the behavior of any shaped dune. And so there's a lot of awkward shaped dunes out there, and I feel this is a significantly more powerful way to think about how dunes respond to vegetation. So in this beginning slide here, all of the dune slices are active, and so they're actively killing vegetation as the dune migrates downwind. So partway through the simulation, you can see that the edges of the dune have begun to host vegetation, and when they become to host vegetation, they become immobilized. And so the dune slices that become immobilized, you can see in the bottom, have vegetation on the crest, and they tend to stop. And they're denoted by the red line as opposed to the yellow line of the active dune slices. And as we get further along in the simulation, only two dune slices here are still active. The center of the dune continues to migrate as the dune slices on the edges successively stabilize inward. And how this occurs is actually a really fascinating geometric feedback, because as the center of that dune continues to migrate downwind, it changes the morphology of the dune slices successively in from the edges, and it makes them more oblique to the wind, which lowers their deposition rates and tends to trigger vegetation growth. And then finally, the dune slices are all stabilized and the dune is immobilized. So our key question here is what caused these dune slices to vegetate? And so the way we answered this question is we went out into real dune fields. And so here, this is a lighter hillshade from White Sands, New Mexico. This is a parabolic dune that is hosting vegetation. And we said that, well, if a dune is hosting vegetation, it must have passed this condition. And our hypothesis really is when a dune field becomes vegetated, every part of the dune field should be just habitable for vegetation. Or you can say, when a dune field becomes vegetated, every dune slice should be just habitable for vegetation. And so we address this question on a really large scale at a number of different dune fields, and so you can read about the results in the paper. And so to answer the question, what is the utility of this knowledge, and what can we do with this information? And so what we're trying to do is generate a framework to predict the future crestline position of dunes in real dune fields. And so this is just a sneak peek at our model that we're developing. This is a crestline model we mentioned in the introduction. And so let's, I'm going to add some dune slices to just kind of explain that this is a crestline that is composed of a number of different dune slices. The blue line is just the outline of the dune. This is a really awkward looking Barkhan dune, and the Salton Sea, this is the Salton Sea, is a very, very arid environment, and what we're going to do is we're going to introduce vegetation to this environment. We're going to increase the vegetation deposition tolerance to stabilize this dune in this this unrealistic future simulation. So let's run forward in time and stabilize the dune. And so you can see the crestline position, morphology of the dune changed shape from a Barkhan dune to a parabolic dune. The center of the dune was the last part of the dune to stabilize. And so that's the idea with our papers. Once we've isolated that condition, when we know vegetation will grow on each dune slice, we can predict the future crestline positions and vegetation cover of dune fields. And we hope you enjoyed the video, and thanks for watching.